In this video, we're going to continue our discussion on linear equations and talk about some applications of linear equations in modeling. Now, anytime you see the word applications or modeling in math, you know what that means, right? It means we're doing word problems today. It's going to take us a little bit to build up to the word problems, but there are going to be a lot of word problems in here, which I know are just everybody's favorite thing to do, so you should really enjoy this video. So let's just start with a definition. Definition is of the point-slope formula, which is also just called point-slope form for a line. So the point-slope formula or point-slope form of a line is given by y minus y1 equals m times x minus x1 in parentheses, where m is the slope and x1, y1 is a point on the line. So this is exactly why this is called the point-slope formula or a point-slope form for the line, because it involves a point and a slope. So if you're asked to write an equation of a line and they give you a slope and a point, this is a good place to start because you just plug stuff in and you're good to go. So we're going to do an example right now where we're finding an equation of a line using this point-slope form. And then we'll change it and write our answer in slope-intercept form, because that seems to be the most popular way to write our linear equations. So example. Let's find an equation of the line passing through the point -5, 2 with slope -3. And then write the answer in slope-intercept form. So last time we did a problem similar to this, and we actually used the slope-intercept form to find the equation right away. We plugged the slope in for m, and then we plugged in -5 and 2 for the y and the x, and then we solved it to find b, and then we had to write our final answer after that. Using the point-slope form first is actually, I think, a little quicker and easier, which is why I happen to be a big fan of point-slope form. So as a reminder, point-slope form is y minus y1 is m times x minus x1. And then we just have to put things in the right places. The x1 and y1 are my x and y coordinates of that point. So I'm going to have a y minus 2 equals, and I'll fill in the m in a little bit, I have x minus my -5. My m is my slope, which they tell me is -3, so I just plug that in right there. So this is already the equation of our line, but this problem asks us to write it in slope-intercept form. So we do need to simplify a little bit. This minus a negative is going to be a plus, we know that already. And also we're going to multiply that -3 through. So I'm going to have a y minus 2 equals -3x. This is a positive 5 times -3, so minus 15. And then to get it in slope-intercept form, all I have to do is add this 2 over to the other side and we'll have our answer. So when I add 2 to the other side, we get our answer in slope-intercept form, y equals -3x minus 13. And there we go, that's all there is to it. Let's do another example, writing an equation of a line, but this time we're going to have to find the slope. We're only going to be given 2 points. So it's a little bit more involved than the one we just did. So next example, write an equation of the line passing through the 2 points, 2, -5, and 7, -3, and write the answer in slope-intercept form. So right now, we can't jump directly into our point slope form like we did in the last example because I don't even know my slope. I just have 2 points. But we can find what the slope is by using our slope formula from last time. Remember that your slope is a y2 minus y1 over x2 minus x1. And I'm going to use my second point as my x1, or my x2 and my y2, and my first point is x1, y1. So this gives me m is -3 minus -5 over 7 minus 2. When I simplify this, I have a 5 in the denominator. -3 minus -5 is -3 plus 5, which is 2. So I have 2/5 for my slope. It doesn't simplify any further than that. So now I have my slope. Now what do? Well, we use point slope form like we just learned. I have a slope of 2/5, and I have a couple points to choose from. And it does not matter which point you use, you'll still get the same answer when you put it in slope-intercept form. So I'm just going to happen to use the first point, just as listed first. Usually I choose whichever point looks easier to me. So for example, if you had a problem where one of the points used only whole numbers and the other point had some fractions in there, you might want to choose the one with whole numbers just because it's a little easier to do that arithmetic. So I'm going to use the point 2, -5. Let me write down what we have so far. My slope is 2/5, and I'm going to use the point 2, -5. All right. So using point slope form, which again is y minus y1 equals m x minus x1. And then we just plug everything in. Y minus a -5 equals my slope times x minus 2. And this, of course, is y plus 5 over on that left side. We do need to distribute our 2/5. We're going to distribute that, which gives me a 2/5 x minus 4/5. So to get this completely into slope-intercept form, I just have to subtract 5. And I'll get y equals 2/5 x, a minus 4/5, and minus 5. Well, minus 5 is the same thing as -25/5. So putting it all together, I have a -29/5 for my y-intercept. There we go. So that is how you use the point slope form to write the equation of a line. Next thing we need to talk about is parallel lines and perpendicular lines. And as I'm sure most of you already are well aware, parallel lines are the lines that do not intersect each other when they're graphed in the same plane. So for example, let me just draw, here's a green line, and here's a red line. And these happen to be parallel because they do not intersect each other. And perpendicular lines are lines that do intersect, but they intersect in a very particular way. When they intersect, they make a right angle, so a 90-degree angle. If this is one of my lines, and then I have a perpendicular line to it, it's going to make a right angle, 90 degrees, where they intersect. So there's a right angle. These are perpendicular lines. Now, why do we care? Well, because parallel lines and perpendicular lines have very special properties regarding their slopes. So let's look at the slopes. We're going to do it on both of these. Let's take care of the parallel lines first. Now remember, slope is talking about the steepness of the line. So I'm going to call this first line, line 1, L1, and the second line is going to be L2. And so I'm going to label their slopes as M1 and M2. Now look at the steepness of those two lines. They look the same. And that's because parallel lines always have the same slope. So I'm going to have my slope M1 is always going to equal my slope M2 if the lines are parallel. So same slope. Now it's not as easy to see the relationship between the slopes in the picture for the perpendicular lines, but what's going on for the perpendicular lines, first we can see that one of the slopes is positive and the other one is negative. So they're opposite in sign. And the thing that's harder to see just from the picture is they're also flipped upside down from each other. They're reciprocals. So my slope M1 is going to be equal to negative 1 over M2. They are opposite reciprocal slopes. So opposite reciprocal slopes. That's what makes parallel lines and perpendicular lines special, is that we know parallel lines always have the same slope, perpendicular lines always have opposite reciprocal slope. So let's use this knowledge to do an example. So our example, we are going to write an equation of the line passing through the point 32 and parallel to the line x plus 3y equals 6. And we're going to write in both slope-intercept and standard form, just for extra practice. All right, so we know that one of the easiest ways to get the equation of a line is to use our brand new point-slope form. But to use that, we need a point and we need a slope. I have the point is 3, 2. And I don't quite have the slope, but I have a means to find the slope. I know that the line that I'm looking for is going to be parallel to this other line. And I know parallel lines have the same slope. So I can take the line they gave me, put it in slope-intercept form so I can find its slope, and that will be the same slope I need for my line. So let's find that slope. This is the line they gave me, and I'm going to put it into slope-intercept form. I'm going to move the x to the other side, and then we get to divide everything by 3. So I get in slope-intercept form, the line they gave me was y equals negative 1/3 x plus 2. What does this mean? It means the slope of the line they gave me is negative 1/3, which means the slope of the line I'm looking for is also negative 1/3 because it's parallel to this, and parallel lines have the same slope. So this m is negative 1/3, and that means that the slope we want is also negative 1/3. So now I'm going to use point slope form. Y minus y1 is m x times, or x minus x1. And now we're going to plug in our point. Our point was the point 3, 2. So I get y minus 2 equals my slope times x minus 3. That is the equation of the line I'm looking for. The problem is it's not in either of the correct forms right now. We want it both in slope-intercept form and in standard form. Let's do the slope-intercept form first. Slope-intercept form we get by distributing that slope, and then we'll end up adding this 2 over to the other side. So I'm going to get a y minus 2 is negative 1/3 x plus 1. And then I'm going to add the 2 to the other side. Y equals negative 1/3 x plus 3. That is the slope-intercept form of this line. Now all that's left is to find the standard form. Remember, the standard form is that ax plus by equals c, and we like to have the a, b, and c as integers. So to put this into standard form, I need to move the 1/3 x to the other side, and I need to get rid of my fractions. So I'm going to start by moving that negative 1/3 x to the other side, and I will get positive 1/3 x plus y equals positive 3. And then I want to get rid of my fractions. To get rid of the fractions, I can just multiply everything by 3. That will get rid of my denominators. So 3 times 1/3 x is x, 3 times y is 3y, and 3 times 3 is 9. And that's how we get our standard form. All right, so that wasn't too bad. There was a lot of steps to follow, but they were all logical steps. So hopefully that wasn't too terrible. Let's do another one very similar to this, except instead of being parallel lines, we're going to do perpendicular lines. So let's write an equation of the line passing through the point -8, -4, and perpendicular to y equals 1/6 x plus 3. Now this problem is actually a little bit easier than the last one, because in the last one we had to figure out the slope of our given line first. This one, the line they gave us, is already in slope-intercept form. So we already know that this slope, 1/6, is the slope of the line they gave us. I want a line that's perpendicular to that. Perpendicular lines have opposite reciprocal slopes. So this means that the slope we want is that 1/6 made negative and flipped upside down. So I get -6 for my slope. Now I have a point and a slope, so we can use our point slope form. Y minus my y1 equals my slope times x minus my x1. And now I'm going to do this the same way we did the last problem. We are going to find it in slope-intercept form and in standard form. So technically, the way this problem was written, we could be finished right now. It didn't tell us to write our answer in any particular way. We're still going to just to get the extra practice in. So we're going to distribute. Be careful with all those negatives. That's where you're most likely to make a mistake. So this is y plus 4 equals -6x. And I have 3 different negatives, so it stays negative 48. And then to put it into slope-intercept form, I just have to subtract that 4 to the other side. and we will get that y equals negative 6x minus 52, I believe. Yep. So we get y equals negative 6x minus 52. That is our slope-intercept form. Now, just for the little bit of extra practice, let's put it in standard form. Again, this one's a little easier than our last problem. Standard form is ax plus by equals c. So I need to move the 6x to the other side. And I get 6x plus y equals negative 52. That is my standard form. There were no fractions in this problem to clear. All right, so now we've done some practice with parallel lines and perpendicular lines and practice using our point slope form. Now it's time for the word problems. So let's start with an example involving speeding tickets. So the example says that a speeding ticket is $100 plus $5 for every mile per hour, so every 1 mile per hour over the speed limit. And the first thing we're going to do is write a linear function to model the cost. S of x in dollars of a speeding ticket for a person driving X miles per hour above the speed limit. All right, so our linear function is going to be named S of x for speeding ticket, and we have x as the number of miles per hour above the limit. So we already know that no matter what, your speeding ticket's going to be at least $100. That $100 stays there every single time. And then it says that we're adding $5 for every single mile per hour above the limit. So if I'm going to write this function, I always have $100, but I also have $5 times the number of miles per hour above the limit. So I get 5x plus 100. That's going to model our cost of the speeding tickets. And then for part B, let's evaluate S of 15 and interpret the meaning. So they want us to figure out what S of 15 is and also say what that means. That's very common in word problems to have to include an explanation of the meaning because this is representing a real world situation, so there is a deeper meaning rather than just a number for an answer. So S of 15, we know from our previous work that that means we have to replace every single x with a 15. So I get S of 15 is equal to 5 times 15, which is 75, plus 100. And so I get 175 as S of 15. Now the question is, what does this mean? And what this means is that a person who's going 15 miles per hour above the speed limit is going to get a ticket of $175. Let me write that down quick. So a person speeding 15 miles per hour above the limit would have a ticket of $175. All right, so this is just one example of a situation that you can model with a linear equation. There are plenty of others. Our next example, we're going to be talking about cost, revenue, and profit. So first we need to discuss what those things actually are, and then we'll do an example using them. So if we're going to model our cost, revenue, and profit. Let's start with talking about a linear cost function. A linear cost function models the cost to produce X items. So for example, let's say that you are running a business and you sell bicycles. You would have a linear cost function to model the cost of producing these bicycles. So a function like that would look like C of X equals MX plus B. I know it looks like that because we set it linear. M is going to be your variable cost, and B is a fixed cost. So like this hypothetical bicycle situation that I just made up, you could have a fixed cost of paying the rent for the building that you produce the bicycles in, and then you have a variable cost for all the materials that are used per bike, something like that. That is our linear cost function. We also have a linear revenue function. So a linear revenue function models the revenue for selling X items. So if we're selling our bicycles at a price of P per bicycle, the revenue looks like P times X, where P is the price per item. This one does not have a y-intercept, a plus b at the end, because you're only going to be making revenue when you actually sell your items. You're not going to have a revenue for selling 0 items. And then we also have our linear profit functions. So revenue is how much money you bring in just from selling the items, but that's not how much money you actually made. Profit is the amount of money that you actually make. That's your revenue minus your cost. So linear profit function models our profit. For producing and selling X items. And your profit function looks like your revenue minus your cost. So we're going to do an example where we're going to use all 3 of these different functions. We have our revenue, we have our cost, and we have our profit function. So this is going to be a fairly long example, and it's yet another word problem because I already know that you are already really wanting another word problem. You love them very, very much. I know that. So let's do another very fun word problem. we have a vendor selling lemonade. So this vendor sells lemonade for $1.50 per cup. The cost to rent the booth is $120, and it costs 40 cents to produce each cup of lemonade. All right, our first part, we want to write a linear cost function. For producing X cups of lemonade. So remember, our linear cost function is all of the cost to us to produce this lemonade. So this is going to include the fixed cost of the $120 for the booth, and it's going to include this 40 cents for every single cup of lemonade that we're producing. Your fixed cost was the B, and your variable cost was the cost per cup. So we have that my cost function is 40 cents per cup, so that's 40 cents times X, plus my fixed cost of $120 for renting the booth. And there is my linear cost function. I'm sure you can guess part B, write a linear revenue function. For selling X cups of lemonade. So your revenue function, remember, is the price per item times the number of items. So in this case, my revenue, since I sell each cup of lemonade for $1.50, my revenue function is 1.50 times my number of cups, so 1.50x. That is my revenue function. I'm sure you can guess part C as well. What is the profit function for this lemonade situation? So write a linear profit function for producing and selling X cups of lemonade. So remember, your profit is your revenue minus your cost. So this is how much money we actually get out of the deal. So I already have my cost function and my revenue function. So my profit function is going to be my revenue minus my cost. So I get profit is my revenue function minus my cost function. Only thing you really have to be careful is make sure you're subtracting all of the cost function. I put parentheses around my cost function to make sure I didn't forget I was subtracting about halfway through. I'm going to simplify this profit function by distributing my negative and then combining my like terms. So I get a minus 0.40x and a minus 120. So I get my profit function is equal to 1.10x minus 120. All right, so the next three parts of this word problem are all going to use this profit function. So you need to make sure you have that written down so you know what I'm referencing when we go back to that all the time. Part D. How much profit will the vendor make? If 50 cups are sold. So this vendor is selling all this lemonade and they managed to sell 50 cups of this lemonade. How much money do they get to go home with after paying for this booth and paying for the cost of all these ingredients? Well, this is the same thing as just evaluating my profit function when x is equal to 50. So P of 50. That's 1.10 times 50 minus 120. And then we just have to simplify this. Now 1.10 times 50 is the same thing as 55. So I get P of 50, my profit when I sell 50 cups of lemonade, is 55 minus $120. So when I simplify this, we find out that this is not a very good situation for us. My profit is negative $65. That means that when this vendor sells 50 cups of lemonade, they lose money, and they lose $65. That is not a good situation. Now, what if I do the same exact thing for part E, except instead of selling 50 cups, we're going to sell 128 cups. So part E, how much profit will the vendor make if 128 cups of this lemonade are sold? Well, we get to do the same thing that we did in part D, except we're evaluating with x equals 128 instead of x equals 50. So I get that my profit when we sell 128 cups of lemonade is 1.10 times that 128 minus 120. Now when I simplify this, the 128 times 1.10, that is equal to 140.8. So my profit when we sell 128 cups, I'm at $140.80 minus $120. And we find out that this time we do make a profit, not a very big profit, 20.8. So that means we make $20.80 by selling 128 cups of lemonade. Not exactly a very huge profit, but at least we're not losing money anymore, so better than nothing. Now, the last part for this question is the most confusing part, I think. Part F says, determine the break-even point. Now, the only reason I think part F is a little more confusing is you might not know what a break-even point is. That is when your revenue and your costs are exactly equal to each other. So you're not making any money, but you're also not losing any money. You just break completely even. You walk away with $0. So the break-even point is when my profit is equal to 0. So we have to solve to find when my profit function is equal to 0. Well, what was my profit function? It was 1.10 times x minus 120, and we're setting that equal to 0 and solving for x, the number of cups of lemonade. So we're going to add 120 to the other side, and then I'm going to divide both sides by 1.10. And when you calculate that, you're going to get 109.090909. It keeps going on forever like that. So this is approximately 109 cups of lemonade. So when this vendor sells about 109 cups of lemonade, not really losing money, not really making money, it's just basically zero. It's not exactly zero in this case because in order for our profit to be exactly zero, we would have to sell 109 and some fraction of a cup of lemonade, and you're not going to sell fractional cups. So we just answer it the best we can in the real world situation. All right, we have one last example for this video because I just can't leave you with only a couple word problems. We need to do one more because they're just so much fun. We always need to do more of them. So let's do one last word problem. Suppose that y represents the average consumer spending on television services per year in dollars. And we're also going to suppose that x represents the number of years since 2004. And the first thing we're going to do is use the data points 2, 308 and 6, 408 to write a linear equation relating y and x. So we're coming up with some sort of linear equation to represent the situation of the cost of TV services for a year. And they gave us 2 data points to use, and we're going to assume this is a linear relationship because they want a linear equation. So we have 2 points and we need a linear equation. First thing we need to do, find the slope between the 2 points. Once we have the slope, we can use our point slope form and rearrange it to get the equation for our straight line. So I know my slope is y2 minus y1, x2 minus x1. And when I fill in these data points I have, I get 408 minus 308 over 6 minus 2. Well, that is 100 over 4, which is 25. So I have a slope of 25, and now I still need to write the linear equation of y and x. We know we need a slope and a point. And we're going to use y minus y1 equals m times x minus x1. And for my x1 and y1, I'm just going to use that first point they gave us, that 2 and 308. So I get y minus 308 equals the slope that I found times x minus 2. And now, just because it's more common to write your answer in slope-intercept form, let's do that. We're going to distribute that 25. So when I distribute my 25, we will have y minus 308 equals 25x minus 50. And then I have to add 308 to both sides. So I get that y is equal to 25x plus 258. That is my linear equation relating x and y. So now we have to remember what it is that we're doing. We're working with a word problem. This is supposed to represent something. So part B wants us to interpret the meaning of the slope. So we need to interpret the meaning of the slope in the context of this problem. First, what is my slope? My slope is my m, which is 25. So my slope of 25, what this means is the consumer spending on TV services rose by $25 per year during this time period. Remember that your slope is your change in y over change in x. So the units for my slope, my y coordinate, my units for the y coordinate was the amount that was spent on TV services, and my x coordinate had units of the years. So this is how much the TV services are increasing per year to figure out the meaning of the slope. Now, part C, we need to interpret the y-intercept. So on this problem, my y-intercept, that was that 258. So my point is 0, 258. That's my y-intercept. And to interpret what this means, we have to talk about what that x-coordinate and what that y-coordinate mean. So what this is saying is the average consumer spending on our TV services was $258 in what year are we talking about? Our x is 0, but remember x is talking about the number of years since 2004. So this is saying the average consumer spent $258 on TV services in the year 2004. Part D, we're going to use the model to estimate the average consumer spending on our TV services for 2007. So we're going to use our model from part A. That was our linear equation. And then we need to plug in a value for our x to represent this year 2007. And then we'll find out what the y value is. That's the average consumer spending. So first, let's rewrite what our model was. We had y is equal to 25x plus 258. The year 2007, that's the same thing as x equals 3, because 2007 is 3 years after 2004. So to figure out the average consumer spending on TV services in 2007, we have to plug in x equals 3. And then just simplify. This tells me y is equal to 75 plus 258. And when I combine those together, I get $333. So we're predicting that the average consumer spending on TV services in the year 2007 would be $333 based on using a linear model and those 2 data points that we have. So that's it for today. If you have any questions, you can feel free to drop them down below and I will answer those as quickly as I can. If you are a current student in my class, you can also email me your questions or come to virtual office hours and we can answer your questions there as well. I will see you on the next video.